In this slide, we will do an exercise to better understand the role of the dispatcher in CPU scheduling. The exercise involves analyzing a Gantt chart that shows the execution of three processes, process A, B, and C over time, based on the provided information. Process A initiated an I/O resource request at instruction cycle 4 and remained in a waiting state for 30 instruction cycles until the I/O resource became available. Similarly, process B made an I/O resource request at instruction cycle 35 and continued waiting for the requested resource for up to 20 instruction cycles. Process A occupies memory addresses from 5000 to 5020, requiring 21 CPU cycles for execution. Process B resides in memory addresses from 7000 to 7050 and demands 51 CPU cycles for completion. Process C occupies memory addresses from 2000 to 2015 and requires 16 CPU cycles for execution. The final process is the dispatcher itself, residing in memory addresses 200 to 204 and requiring only 5 CPU cycles for execution. Considering the given information, we are instructed to complete the Gantt chart in Figure 5 in the next slide, based on process state transitions for up to 70 instruction cycles. Each process is assumed to execute for a maximum of 6 instruction cycles before being interrupted by an I/O request. Utilizing the instructions and information from the dispatch exercise in the previous slide, we must now complete this Gantt chart. Employ this Gantt chart to visualize the status of processes A, B, C, and the dispatcher within 70 instruction cycles, indicating whether each process is in a running, ready, or blocked state. To proceed, please pause this video and attempt to complete the Gantt chart using the information provided in the previous slide. This slide and the next slide will show the answer of this exercise. Based on the information from previous slides, there are 3 processes which are process A, B, and C. The maximum CPU time for each process to run is 6 instruction cycles. We started with process A to run. Process B and C are waiting in queue in ready mode, but at instruction cycle 4, process A is requesting I/O resource and waiting for another 30 instruction cycles. So, at the 4th instruction cycle, dispatcher take over CPU resource and process A is blocked from using CPU resource within 30 instruction cycles. Then dispatcher assign the CPU resource to process B to run in 6 instruction cycles. After 6 instruction cycles, process B will stop to run and back to ready mode. Dispatcher take over to use CPU resource for 5 instruction cycle to assign the next process to use CPU resource, which is process C. Process C start running within 6 instruction cycles and stop after that. Dispatcher take over again the CPU resource and process C back to ready mode. At this time, process A is still in block mode because it is still waiting or running for requested I/O resource. So, dispatcher process to pass CPU resource to process B. Process B is back to running mode, but at the 4 instruction cycles, process B is requesting for I/O at instruction cycle 35 and waiting for the resource within 20 instruction cycles. Upon process B entering the blocked state, the dispatcher regains control of the CPU resource for 5 instruction cycles to determine the next process to execute. Process C, currently in ready mode, transitions to the running state and executes for another 6 instruction cycles. After process C completed to run for another 6 CPU cycles, dispatcher take over again the CPU resource for 5 instruction cycles to determine the next process to run, which is process A, to run for another 6 instruction cycles because of its turn based on sequence and process A is in ready state. After process A runs for another 6 instruction cycles, The dispatcher regains control of the CPU to choose the next process to run. Instead of picking process B, which is still in waiting state, the dispatcher selects process C. Process C executes for 4 instruction cycles, completing its execution with a total of 16 instruction cycles. In this Gantt chart, the yellow blocks represent the dispatcher process's running state to distinguish it from other processes. You can complete the Gantt chart by indicating the ready state of the dispatcher process on its existing bar. However, this is not mandatory. By examining the completed Gantt chart, we can extract several key pieces of information. One such piece of information is the number of cycles executed by each process within the 70 instruction cycle time frame. For instance, process A managed to complete 10 cycles within the 70 instruction cycle time frame. Similarly, process B also successfully executed 10 cycles within the 70 instruction cycle time frame. Notably, process C managed to execute 16 cycles within the 70 instruction cycle time frame. As evident from the Gantt chart, only process C successfully completed its execution within the 70 instruction cycle time frame. Regrettably, both process A and process B failed to complete their execution within the 70 instruction cycle time frame. This is primarily attributed to the fact that, based on the provided information, process A requires 21 cycles to complete, process B requires 51 cycles to complete, and process C requires 16 cycles to complete. The dispatcher Gantt chart allows us to determine the state of each process at a specific instruction cycle time. For instance, during instruction cycle 4, which is labeled as X time, process A is in the running state, while process B and process C are in the ready state. Conversely, during instruction cycle 19, which is labeled as Y time, process A and process C are in the ready state, whereas process B is in a waiting or blocked state. Finally, at instruction cycle 38, which is labeled as C time, process A remains in the running state, process B continues to be in a waiting or blocked state, and process C persists in the ready state.